Good day, everyone. So welcome back to the second part of our review and lecture on lipid metabolism. So for this review, we shall discuss the mobilization and oxidation of fatty acids, followed by its synthesis and desaturation. Then we'll end this part with a comparison between these two opposing processes, oxidation and synthesis. So we all know that triacylglycerol is a major source of energy. It makes up 90% of our dietary lipids. When completely oxidized, it yields carbon dioxide and water, and that releases a lot of energy, 6 times more energy compared to an equal weight of glycogen. In order for us to absorb lipids, they have to be digested at the lipid-water interface, which means lipids have to be emulsified by biosalts and bioacids in the small intestine prior to their absorption. For our discussion on metabolism of fatty acid, we will be using palmitic acid as a representative fatty acid. Palmitic acid is called hexadecanoic acid because it does contain 16 carbons. So how is fatty acid metabolism regulated? The two processes that we shall be discussing today, synthesis and oxidation, are opposites of each other, which means they have to be mutually controlled. When one is turned on, the other one is turned off. In the fed state, storage of fatty acid is favored, and carbohydrates are used as metabolic fuel. However, in the fasting state, fatty acid mobilization and oxidation is favored in place of glucose, which may have gone down during fasting states. Let's start our discussion now on fatty acid mobilization and oxidation. Triacylglycerol are stored in adipocytes. When the amount of glucose is no longer enough to provide metabolic fuel, the fatty acids are released in order to supply for this energy demands. It is the enzyme hormone-sensitive lipase that hydrolyzes the triacylglycerol to yield free fatty acids and glycerol. This, of course, occurs at two conditions: at low carbohydrate concentration and low insulin concentration, as well as when there is increased levels of the hormone epinephrine. So how does epinephrine now mobilize the fatty acids in adipocytes? Let's imagine this as the adipocyte. On the cell membrane, we will find beta-adrenergic receptor. Say, for example, you've been very active or you have been exercising. The release in epinephrine causes this particular hormone to bind to the beta-adrenergic receptor. This now in turn activates a series of kinases. One of them is a protein kinase, which phosphorylates and activates the enzyme hormone-sensitive lipase. In its active form, it catalyzes the hydrolysis of triacylglycerol to free fatty acids as well as glycerol. Now, those fatty acids will not stay on the adipose tissue, but rather they will be transported down to albumin to the following organs for beta oxidation. What are the two organs where fatty acid oxidation takes place? These are the liver and the skeletal muscle. As a matter of fact, the skeletal muscle is one of the organs that utilizes a lot of fatty acid as a metabolic fuel. We can divide fatty acid oxidation into 3 major stages. Number 1, the activation of fatty acid in the cytosol of the liver as well as the skeletal muscle. Number 2, its transport into the mitochondria. And number 3, the beta oxidation that actually takes place in the mitochondrial matrix. Let's start first with the activation of fatty acid. The active form of fatty acid is called the fatty acyl-CoA. This activation occurs in the cytosol, wherein the fatty acids are esterified to COASH as catalyzed by the enzyme acyl-CoA synthetase, as illustrated in this particular biochemical reaction. The process requires the expenditure of 2 ATP, since ATP is hydrolyzed to AMP and to inorganic phosphate. Once active, this fatty acyl-CoA should be transported into the mitochondria. But first, it needs a carrier. And what is this carrier? This carrier is called carnitine. If you take a look at the structure of a carnitine, it contains a carboxyl functional group as well as an amino group, which means carnitine is an amino acid. However, it is not the regular amino acid, since these two functional groups are not located on the same alpha carbon. Let's take a look now at how carnitine and fatty acids are translocated into the mitochondria. So the free carnitine is linked to the fatty acid, liberating now the COASH that was initially attached to it. What you get is a fatty acid carnitine complex. The process is catalyzed by the enzyme carnitine palmitoyl transferase 1. This complex is translocated inside a mitochondrial matrix in exchange for free carnitine by passing through a carnitine carrier protein. Inside the mitochondria, the fatty acid is reattached to COASH, liberating now the carnitine that was initially linked to it. This fatty acid CoA complex is the one that will undergo beta oxidation. Let's take a look at an overview of beta oxidation first. Like what I have said earlier, fatty acid that will be used as a representative fatty acid here is palmitic acid, which contains 16 carbons. The slash arrow downward represents one round of beta oxidation. Now, since palmitic acid contains 16 carbons, palmitic acid will undergo a total of 7 rounds of beta oxidation. Each round of beta oxidation is composed of 4 steps. So what are the 4 steps that make up one round of beta oxidation? Let's enumerate them. The first step is oxidation, which yields fat H2. The second step is hydration, which involves a water molecule. The third step is another oxidation, but this time the electron carrier that is generated is NADH. And finally, the final step is cleavage or thiolysis. Let's take a look now at the first step. So we all know that oxidation is either the gain of oxygen or loss of hydrogen with eventual loss of electron as well. So the first question is, why is it called beta oxidation? Let's backtrack a little bit. So the first step let's restart once more with enumerating the different steps, the 4 steps in one round of beta oxidation. The first step is called oxidation, which involves release of fat H2, followed by hydration, oxidation, but this time what is released as an electron carrier is NADH. And the final step is cleavage or thiolysis. Let's move on to the first step of beta oxidation. The first question is, why is it referred to as beta oxidation? If you remember the numbering system for fatty acid, this is referred to as the delta carbon, alpha, and the beta carbon. It is the beta carbon that will undergo the oxidation process. If you remember as well, oxidation is either gain of oxygen or loss of hydrogen together with loss of electron. In this case, it is the beta carbon that will lose the electron as well as the hydrogen. This hydrogen, as well as this hydrogen, will be lost together with electrons, and those electrons are captured by fat, becoming fat H2. What you have now is a trans fatty acid. This fatty acid will undergo the next step, which is oxidation. A water molecule will be incorporated into the double bond. So what you have is a hydrated fatty acid. So this is actually OH. The second step is another round of oxidation. The hydrogen, the two hydrogens on the beta carbon, will be released together with electron. It's captured by NAD, becoming NADH2. So what you have now is a keto acid. And the final step is thiolysis or cleavage. The bond between the alpha and the beta carbon is going to be cut off with incorporation of COASH to this particular fragment. This fragment over here is what we call acetyl-CoA, whereas this fragment over here is the fatty acid that is now shorter by 2 carbons. What will happen now to these products? One possible fate for acetyl-CoA is that it can enter the Krebs cycle and generate even more reducing equivalents and ultimately ATP. What about the fatty acid that is now shorter by 2 carbons? It will undergo the same 4 steps, another round of beta oxidation, until all the 2 carbon fragments are cleaved off. What about the fat H2 and the NADH? Now remember that this reducing equivalents will eventually travel to the electron transport chain, where fat H2 can generate 2.5 ATP, or in modern books, it's actually 1.5 ATP if you want to be very precise. Whereas NADH2 will generate 3 ATP on the electron transport chain, or if you wish to be very precise, it will generate 2.5 ATP on the electron transport chain. Let's now take a look at the energy balance of beta oxidation. How many acetyl-CoA, NADH, and fat H will be generated? So let's take a look at palmitic acid here. Each slice downward represents 1 round of beta oxidation, which is made up of the 4 steps we have mentioned, and we have here the scorecard. We'll count how many acetyl-CoA, NADH, and fat H2 are generated with each round. So in the first round of beta oxidation, we generate 1 acetyl-CoA, 1 NADH2, and 1 fat H2. So now what we have is an acid that is shorter by 2 carbons. It's now a 14 carbon fatty acid. It will undergo the next round of beta oxidation. After this round, there's now a total of 2 acetyl-CoA, 2 NADH, and 2 fat H2. Third round, 3 acetyl-CoA in total, 3 NADH, and 3 FATH2. Round 4, 4 acetyl-CoA, 4 NADH, 4 FATH2. Fifth round, 5 acetyl-CoA, 5 NADH2, FATH2. Sixth round, 6 acetyl-CoA, 6 NADH2, 6 FATH2. And finally, we have the last, the seventh round. If this is cleaved, this will generate 2 acetyl-CoA. So in total, we have a total of 8 acetyl-CoA, 7 NADH, and 7 FATH2 with a complete oxidation of palmitic acid. What happens now to the acetyl-CoA that are produced with each round of beta oxidation? Most of the acetyl-CoA from beta oxidation enters the Krebs cycle. However, when they can no longer enter the Krebs cycle, some of them form ketone bodies. So what are the 3 ketone bodies? This includes acetoacetate, beta-hydroxybutyrate, and acetone. So this reaction is actually taking place in the mitochondria of the liver. This requires numerous amounts of acetyl-CoA. So in the first step, there's condensation of 2 acetyl molecule, yielding now acetyl-CoA. A third acetyl-CoA is condensed with the acetyl-CoA, yielding beta-hydroxymethyl-glutaryl-CoA, or HMG-CoA for short. This is the same HMG-CoA that is produced in the early steps of cholesterol biosynthesis. The difference, however, is that this particular process is taking place in the mitochondria of the liver, whereas the HMG-CoA produced in cholesterol biosynthesis is taking place in the cytosol of the liver. The HMG-CoA now will become the precursor for the production of the 3 ketone bodies, namely acetoacetate, which can be converted into acetone, or it can also be converted to beta-hydroxybutyrate. As you can see in this particular pathway of ketogenesis, it requires the presence of several acetyl-CoA. So these ketone bodies are produced in the liver. Eventually, they are exported out, where they will travel into the brain, into the heart, and are utilized as metabolic fuel by entering the Krebs cycle in the form of acetyl-CoA. So ketone bodies are actually very important, especially during prolonged starvation, where the ketone bodies can provide 70% of the energy requirement of the brain. So remember that the brain utilizes only 2 metabolic fuel. The preferred metabolic fuel is still glucose. When glucose is no longer available or is in limited supply, like during starvation, the next metabolic fuel is not fatty acid itself, but rather ketone bodies. We do produce ketone bodies under normal circumstances, however, but it is only up to 1 milligram per ml because the kidney can excrete up to 20 milligrams per day. However, during prolonged starvation and in uncontrolled diabetes mellitus, the excessive production of ketone bodies can cause ketoacidosis, which may be lethal because it can cause cerebral edema and ultimately death. What about the oxidation of odd-chain fatty acids? Most naturally occurring fatty acids are even-numbered. However, there are some odd-numbered fatty acids which can be rare. These are found in some plants and marine organisms. So if you do regularly ingest food products from marine organisms or for some plants, we may be able to acquire odd-chain fatty acids. But they are actually, we are capable of utilizing them as metabolic fuel in the same process that we use even-numbered fatty acid. They will undergo the same steps in beta oxidation. However, in the final round of beta oxidation, what is yielded is propionyl-CoA. And eventually propionyl-CoA is converted to succinyl-CoA, which again can enter the Krebs cycle or the tricarboxylic acid cycle. So why does it produce propionate in the final stage or round of beta oxidation? So we have here a schematic representation of an odd chain fatty acid. It contains 17 carbons. Sorry, it actually contains 15 carbons. Each slice downward represents one round of beta oxidation. So as you can see, we are able to produce 7 acetyl-CoA, 7 NADH, 7 fat H2. But the final fragment is a 3-carbon molecule. We call that propionate. What about unsaturated fatty acids? Are we capable of metabolizing unsaturated fatty acid and using it as a metabolic fuel? We can. It will undergo the same beta oxidation until a few carbons before the double bond. Upon reaching the double bond, 2 carbons before the double bond, the cis configuration of the fatty acid is isomerized to the trans configuration. And then it will undergo beta oxidation, continue with the beta oxidation. So the bottom line is that during beta oxidation, cis fatty acids are converted to trans fatty acid and will undergo the same steps now in beta oxidation. Let's take a look at how fatty acid oxidation is controlled. Let's start first on the fed state. On the fed state, the hormone insulin goes up. Insulin itself is an inhibitor of the hydrolysis of stored triacylglycerol. So with high carbohydrate intake, there is no mobilization of the fatty acids in adipose tissue. Now, what about for those fatty acids that are already in the muscle and in the liver? Can they undergo beta oxidation? Well, unfortunately, no, because insulin itself stimulates the formation of malonyl-CoA, which is known as an inhibitor of carnitine palmitoyl transferase 1, the enzyme that links carnitine with the fatty acid. So in other words, the fatty acid remains in the cytosol and is not transported into the mitochondria. So there would be no beta oxidation. Now, what about in the fasting state? 2 hormones go up in the fasting state. One is epinephrine and glucagon. So epinephrine doesn't just rise in fasting state, it is also the hormone that goes up when one is very active. It activates the enzyme hormone-sensitive lipase, which we have discussed in the early parts of our lecture here. And as you know, the hormone-sensitive lipase enzyme hydrolyzes the triacylglycerol in the adipose tissue, allowing them to be mobilized. Once the fatty acid reaches now the liver and the skeletal muscle, they can undergo beta oxidation because glucagon inactivates malonyl-CoA, which means there is no inhibitor now for the enzyme carnitine palmitoyl transferase 1. So carnitine can be linked to the fatty acid This now leads to increased transport of fatty acid into the mitochondria, and beta oxidation pathway can occur. Let's now take a look at the control points for fatty acid oxidation. Rather, let's continue now with fatty acid synthesis, elongation, and desaturation. Fatty acid synthesis occurs mainly in 3 organs. That includes the liver, adipocytes, as well as the mammary gland of pregnant and lactating women. This is because fatty acid is needed as a component of milk. What is the precursor now for fatty acid synthesis? That would be excess acetyl-CoA. So if you have a lot of caloric intake and is very sedentary, the acetyl-CoA, instead of entering the Krebs cycle, would rather just link together and be used as a precursor for the production of both fatty acid and cholesterol. Reducing equivalents are needed in the synthesis of fatty acid. This would be NADPH, which of course mainly comes from pentose phosphate pathway. Fatty acid synthesis and degradation occur by separate pathways. Synthesis occurs in the cytosol, whereas degradation occurs in the mitochondrial matrix. The overall reaction for fatty acid synthesis is shown here. As always, our representative fatty acid is palmitic acid, which contains 16 carbons. Or rather, 16 carbons. So if we need 16 carbons, this means that we need a total of 8 acetyl-CoA. But only one is shown here because the other 7 acetyl-CoA are used to produce malonyl-CoA, 7 malonyl-CoA. Malonyl-CoA is actually a derivative of acetyl-CoA. 14 NADPH are also required. There are only 2 main enzymes in fatty acid synthesis. 90% of the pathway is catalyzed by one single enzyme, a large multimeric enzyme called fatty acid synthetase. Whereas the first step of fatty acid synthesis is catalyzed by the regulatory enzyme called acetyl-CoA carboxylase. The other coenzymes and cofactors that are needed include biotin, NADPH, magnesium, as well as manganese. Fatty acid synthesis can be likened to the reversal of beta oxidation. We can also divide it into 3 stages, namely loading of the precursor via ester derivatives. Now we'll explain what that means in a little while. Condensation of precursor, reduction, dehydration, and reduction. Now remember, the 4 steps in beta oxidation are oxidation, hydration, oxidation, and thiolysis or cleavage. If we reverse that, as well as reverse its order, the reversal of it would be condensation, the opposite of cleavage or thiolysis. Reduction, the opposite of oxidation. Dehydration is the opposite of hydration. And oxidation, reduction is the opposite of oxidation. Let's start first now with the loading of precursor via thioester derivatives. Like what I said earlier, one of the enzymes in fatty acid synthesis is a large multimeric enzyme called fatty acid synthase. It's composed of several subunits. One of them is referred to as acyl carrier protein, or ACP for short. It contains sulfhydryl group, which is the attachment site for the precursor malonyl-CoA via thioester linkage. So there is another thioester linkage found in another domain. In this discussion, let's just call this as the small tower, or as ACP, let's just refer to it as the large tower in this discussion. Of course, we need the two precursors, namely the two carbon molecule called acetyl-CoA and its derivative, the three carbon molecule called malonyl-CoA. If we compare acetyl-CoA and malonyl-CoA, we can see that malonyl-CoA is simply acetyl-CoA with an extra carboxyl functional group, which means if we are going to synthesize malonyl-CoA from acetyl-CoA, all we need to do is attach a carboxyl acid to acetyl-CoA, as shown by this particular reaction. The first step prior to loading, the first step in fatty acid synthesis, the formation of malonyl-CoA from acetyl-CoA. So acetyl-CoA is converted into malonyl-CoA by simple attachment of carboxyl functional group. This can come from carbon dioxide. Requires expenditure of ATP and catalyzed by the enzyme acetyl-CoA carboxylase. Going back now to the loading process, acetyl-CoA is linked to the small tower, while malonyl-CoA is linked to the large tower. What follows after loading? Acetyl-CoA will be condensed with malonyl-CoA. There is condensation, throwing away the carboxyl functional group that was initially attached. What follows after this? The next stage is reduction, dehydration, reduction. The goal is to take out this oxygen so that this part, which ultimately will become the hydrocarbon tail of a fatty acid, is composed exclusively of carbon dioxide and hydrogen. So how is this oxygen taken out? That involves reduction, introduction of hydrogen and electron coming from NADPH. So now the double bond O becomes OH. Next, the hydroxyl functional group has to be taken out so that, again, it's a purely hydrocarbon tail. This involves dehydration. The double bond has to be taken out so that what you have in the end is a saturated fatty acid. This involves the final round or another reduction step, gain of hydrogen. And that hydrogen comes from NADPH. So what you have here now is a short chain fatty acid, a 4-carbon short chain fatty acid called butyric acid. But our goal here is to produce a long chain fatty acid, palmitic acid, so that those 3 stages will be repeated once more until we have produced a 16-carbon palmitic acid. So butyric acid will be transferred. So ACP will be free and ready to accept malonyl-CoA number 2. This is loading, followed by condensation of butyric acid with malonyl-CoA, throwing away the carbon dioxide again that was initially attached to it. Next step is removal of oxygen in what would turn out to be the hydrocarbon tail. So this would involve reduction, dehydration, reduction. So what you have now here is a 6-carbon short chain fatty acid, which means the process has to be repeated again. Short chain fatty acid will be transferred so that ACP can accept another malonyl-CoA. Number 3, loading. So this will be followed by condensation. Take this out via reduction, dehydration, reduction. Those steps will be repeated again. Loading, condensation, reduction, dehydration, followed by reduction. Loading of malonyl-CoA number 5, followed by condensation, reduction, dehydration, reduction. Loading of malonyl-CoA number 6, followed by condensation. Take this out by reduction, dehydration, reduction. And finally, we load the final malonyl-CoA, number 7, followed by condensation, reduction, dehydration, and reduction. So this eventually will be released. What you have now is a 16-carbon palmitic acid. Take note that this is the carboxyl functional group, whereas this is the saturated hydrocarbon tail. This is how it is often represented in our references and reviewers, where highlighted in yellow is the step catalyzed by acetyl-CoA carboxylase, the initial step. As highlighted in blue is the step catalyzed by the enzyme fatty acyl synthetase. Let's take a look at the different steps one by one. Acetyl-CoA is converted into malonyl-CoA by attachment of carbon dioxide. This is catalyzed by acetyl-CoA carboxylase, the regulatory enzyme. Biotin is required as a cofactor for this particular step. Malonyl-CoA is linked to the ACP domain of fatty acid synthase. Malonyl-CoA condenses with acetyl-CoA, throwing away the carbon dioxide that was initially attached to it. What you have is acetyl-CoA. Next, this oxygen has to be taken out by reduction, forming now OH, with NADPH as the source of hydrogen and electron. Take out this OH functional group by dehydration, and then take out this double bond by another round of reduction, with NADPH as the source of hydrogen and electron. The butyric acid will undergo the same process of condensation, reduction, dehydration, reduction, repeated all over again for 7 more times until 16 carbon fatty acid is produced. If everything is too much to remember, the good news is the most important step that you need to remember here is just the first step, the step catalyzed by acetyl-CoA carboxylase. So this enzyme catalyzes the first and the committed step of fatty acid synthesis. Like what I have said earlier, it is biotin dependent. It can be inhibited by increased fatty acid concentration, as well as it is hormonally regulated, mainly by glucagon and epinephrine, which promotes the phosphorylation and eventual inactivation of the enzyme. So when you are hungry, when your blood glucose is low, glucagon goes up. When you're fasting, glucagon goes up. When you're active, epinephrine also goes up. These two hormones activate a series of protein kinases that phosphorylates the active enzyme into its inactive form. Once inactive, there is no fatty acid synthesis. So when you are exercising or when you are controlling the amount of your caloric intake, no fatty acid synthesis takes place. However, your blood sugar is very high because you have a lot of carbohydrate intake. Insulin goes up. This activates phosphatase, which now dephosphorylates the enzyme and renders it active. So there would be fatty acid synthesis. So in other words, excessive carbohydrate intake promotes fatty acid synthesis and will make you fat. How about unsaturated fatty acids? Are we capable of producing unsaturated fatty acids? Of course. That would depend on the position. The place takes place. The process rather takes place in the smooth endoplasmic reticulum. Humans and other mammals have 4 desaturases, namely delta 9, delta 6, delta 5, and delta 4 fatty acyl-CoA desaturase. Now, mammals cannot incorporate a double bond beyond delta 9. Positions that are beyond delta 9 include omega-3 and omega-6. And this is the reason why omega-3 and omega-6 fatty acids are essential. Let's end the discussion by comparing beta oxidation and biosynthesis in terms of location, tri-ester linkage, the 2 carbon fragments that are generated, the electron carrier, and energy alteration. Like what we have discussed, beta oxidation takes place in the mitochondrial matrix of liver and skeletal muscle, whereas biosynthesis takes place in the cytoplasm of the liver, adipose tissue, and mammary gland of lactating women. What about the tri-ester linkage? Fatty acid is linked to COASH, whereas in biosynthesis, malonyl-CoA is linked to acyl carrier protein, part of fatty acid synthase. The 2 carbon fragments that are generated in each round of beta oxidation is acetyl-CoA. Whereas in biosynthesis, what is linked together are malonyl-CoA, which is a derivative of acetyl-CoA. Each round of beta oxidation produces FADH2 and NADH, whereas in biosynthesis, each round consumes NADPH. Finally, the energy alteration. For palmitic acid, it yields a total of 129 ATP. On the other hand, for biosynthesis, the overall process for the production of palmitic acid consumes 7 ATP and 14 NADPH. We shall be continuing with the final part of lipid metabolism in a little while.